that reason that you can see a variety of different forms for periodic tables. Most commonly, though, we see the lower left-hand corner. That tends to be the default. The other ones are kind of random and sporadic depending on what people are attempting to try and show in their organization. So let's go ahead and start with where it all comes from. So if we go back 1829, I mean, we can go back a little bit earlier with Dalton, because Dalton had his first periodic table, but it was just a list of elements. When we get to Dobreiner, he's starting to organize those elements according to different classes. And so his first observation was that they could be organized according to triads. I don't know if it's actually true or not, but organizing based off of triads isn't a bad idea, at least if you consider potentially the historical context. A lot of what humans go through and do is try to find patterns. Well, think about where we've seen groups of three before, particularly in older societies with a perhaps larger investment in Christianity. Father, Son, Holy Ghost is a possibility. Again, I don't know, but that's something I like to think of as kind of a potential here. We're looking for those patterns. 1865, Newlands goes through and says that actually groups of three doesn't really make sense. They should be organized according to groups of seven. Okay, and that may seem weird. Why this big sudden shift? Well, that shift is probably due to a vast increase in the number of elements that were discovered, and with that vast increase, the groups of three didn't quite work out. So we needed a new pattern. So why groups of seven? Because that also seems kind of like a random number to pull out. Remember, humans are looking for patterns. And at this stage in the game, we knew music. And what we knew from music was octaves. And we've got the law of octaves. The eighth note, I think. I usually rely on students to help correct me on this one because I'm not a musician. The eighth note is repeating the set. So he organized the periodic table according to these octaves, which made sense because that's reflected in what we understand of music. Okay, so all of these kind of patterns are coming through and kind of sticking with it. While those discoveries are interesting and those names might be cool if you were in a random trivia contest, I don't expect you to have those memorized. What I do expect you to memorize is this guy's name, Mendeleev. And Mendeleev wins out when we're talking about the periodic table. And it's not just because he found patterns, because like we saw, Newlands found patterns, Dobreiner found patterns. Why do we not remember them? Well, Mendeleev's periodic table, he organized according to atomic mass. And the big reason that we give Mendeleev so much credit happens right about here. Except that was the wrong button, so let me try that again. Happens right about here. When we're looking at our periodic table that we've got here, you'll notice that Eka as an element shows up multiple times, and that seems a bit weird. Take with that not only does it show up multiple times, it's not showing up in the standard element symbol format. We're not seeing a capital letter followed by a lowercase, or even just a capital letter. We're seeing these three-letter code, Eka, and a dash. Well, where is that coming from? What is the point of that? Well, Eka meant similar to. Okay, so why Mendeleev were given so much credit was not that he found patterns, but that he could look at the patterns and saw holes. That there were holes in the periodic table. And so that when he put it together, he was like, an element belongs there. I don't know what it is, but something should be there. You people that do all that sciencey find stuff, me as a theoretician is going to tell you, you screwed up and you haven't found something. It belongs there. That's kind of cool to be able to look at patterns and recognize that there is something missing from the data set. That's pretty phenomenal. But he did take it a little bit further, which is even more interesting. Not only did he go through and say that you're missing something, but he actually told people what they were missing. What information about that thing that no one knew they needed to find. Okay, and so one of the classic examples of this, or the example that at least our textbook referenced, is looking at the discovery of eka silicon. which was later discovered to be germanium, or named to be germanium. So ecosilicon, similar to silicon. He predicted it in 1869, and the actual element was discovered 1886. Okay, so let's just round, say 30 years. So to give you an idea of this, if I told you right now in 30 years, you would have the same skin color. You'd be like, well, duh, that was an obvious one. Okay, well, that's what Mendeleev did. He said the color of the element will be gray. Most elements are gray, so not a big deal. But then I also added and said your weight will be 162 grams. He did that too. Okay, that's starting to get a bit spooky. Okay, but you look at someone, you can approximate their weight. Okay, your body fat, the ratio of fat to muscle, whatever, let's pick a number. 18.4, that's really low. That would be pretty healthy. 18.4%, boom. He's nailing the density, okay, on the substance. Melting point, yeah, you got to give him a little bit of leeway. You just said very high. Okay, that's not super descriptive, but 937 degrees Celsius, that's pretty high. So that makes sense. But not only in 30 years, you will have a spouse. Okay, he was able to predict that. What would the pattern be with this element interacted with oxygen? That's kind of neat. Not only that, but the combined body fat, new value. So get the idea behind this. 30 years, we're coming up with some pretty insane predictions behind this. Okay, and it is that kind of predictive ability of Mendeleev's periodic table that we really give him credit. Okay, and that's why we remember him as the kind of the father of the periodic table. Okay, he did make some pretty serious mistakes, but we tend to ignore those mistakes. Okay, for the large part. He was also a crazy dude. If you're interested in crazy Russian dudes, take a look at Mendeleev and read up on him because he's kind of cool. I do want to call attention to one thing. He organized his periodic table according to atomic mass, and that is not how our periodic table is organized. So that's one of his big mistakes. Okay, and we'll see how that got fixed here in a little bit. As we continue through history, Ramsay's kind of the one that provides the not last missing piece, but a last big chunk of the periodic table, and that was the discovery of argon, followed very swiftly by helium, neon, krypton, and xenon. Okay, and radon. These are all what are known as the noble gases. Okay, gases aren't easy to trap or work with or see, so being able to find these makes sense that it took a while to get a hold of them. Okay, but that then brings in a whole nother column on our periodic table. The other reason why these are difficult and why we call them noble is they don't interact with things. There are some gases that interact with a lot of things, and so we triggered those elements pretty quickly on. Oxygen. Okay, we discovered oxygen very, very swiftly. But the noble gases, because they didn't interact with anything, it took a little bit longer to nail down. That same kind of pattern holds true for a lot of other kind of scientific discoveries. One of the ones that jumps to mind, glucose. Interesting one. There's two forms of glucose, alpha and beta. Why do we call them alpha and beta? Well, first and second were already used. So alpha A, first in the letter in the Greek alphabet, there it goes. And it was more reactive than glucose beta. So yeah, in any case, Moseley, 1913. So now we're beyond the discovery of an atom, okay, atomic structure. And so when Moseley was going through and looking at Mendeleev's patterns, he noted that there were some weird kind of exceptions and mismatches, and you can go through the periodic table and find those mismatches with mass. Atomic mass isn't a perfect alignment of the elements. Nuclear charge is a much better way to group the elements, and it actually picks up patterns a lot better and more consistently, as we'll see in 2 videos probably, maybe even 3. So he said that everything should be organized by nuclear charge rather than atomic mass, and then that matched up the trends almost spot on perfect, and that's where we end up with the periodic table that we're used to today. Okay, and periodic law comes from Moseley. increasing atomic number. Okay. Yeah, so there's our periodic table. There's a lot more information that's embedded in it. Okay, a lot of those patterns, we'll look at examples in this video and then in a couple other ones. It's ridiculous the amount of stuff that's stashed within this thing. Okay, and that's one of the things you're going to learn this semester is how to pull some of that information out, and really this unit. Okay, so getting up a labeling system behind our periodic table. So the first thing is it's noted out in kind of a grid section. So we've got vertical columns, so that's on that vertical part, and then we got our horizontal rows. The horizontal rows represent a period or named a period or a series. Okay, the vertical columns are typically referenced as a group or a family. Okay, and they're named for those things for particular reasons because we see kind of patterns behind those. Okay, and that's why you should know how to reference periods versus groups. Particular families within the periodic table get different names. So if we go through and take a look, we've got, come on pen, that very first column is known as our alkali metals. Okay, these were already metals because if we looked at our staircase, they were to the left of the staircase. So it's a bit redundant to call it metals. So I'm just going to erase metals and we'll see why here in a second. And I'll erase metals in the second one. Because when we move to the next one, we're of course going to get another name. And so alkaline earth. I always got these two backwards until I realized, like 5 years ago, alkali, one word, first column. Alkaline earth, two words, second column. That's where the pattern stops. But hey, if it helps you to remember alkali versus alkaline earth and which one's which, that works out for you. It's not hugely important to nail that down. Like I said, I really only defined that or differentiated that within the last 5 years. And I've been doing chemistry and taking chemistry classes for 20 years. Sure, let's stick with 20. The next big kind of section of the periodic table, we're not going based off of a group. We're just calling this whole middle section here as our transition elements. Okay, and we'll reference those later. And then we move out to the far right-hand side. So those were our transition elements. You can box in green. Because we're right next to it, we do have the inner transition elements down at the very bottom. We rarely, if ever, study those because they're so radioactive. So I would argue it's not worth your time to deal with those. If you want to do it just because you want to say you're cool, that's fine. Go ahead and do so, but you don't need to for my sake. We get the noble gases. Okay, that was all which scientist? Yeah, that was all due to Ramses, discovering pretty much all of those and some of his partners. Then we get the halogens in the column right next to it. And what we've now identified are all the really kind of critical elements to have named, or the sections to name. We've got our alkali metals, alkaline earth, transition elements, noble gases, and halogens. After that, just because I think it's fun to add some kind of random stuff, this column with oxygen as its lead, it's just kind of fun to say, it's known as the chalcogens. And then if we want to throw in an extra fun one, the nitrogen column right next to it, and this is even more fun, whoa, this is even more fun to say, this is the pnictogens, which I can't spell, okay? This is just kind of fun, pnictogens. Random kind of facts if you're into that kind of cool stuff. Last thing I'll reference, because you'll hear it talked about, so let me clear everything away. And then I'll also clear most of that away too, because we don't need that. As you'll see at the very bottom now of the screen, we've got this thing called the representative elements. The representative elements are referring to the first two columns and the last 6 columns. Those are our representative elements. Okay, not a huge deal to know that those are called the representative elements, but you will see reference to those. Okay, so we've got some names behind our periodic table or our different columns of the periodic table, so that's neat. If if we go ahead and continue on, I want to get you kind of thinking about these physical properties and what kind of trends we can see within them. Okay, so what we've got here is a table with a bunch of different properties of some elements. And if, you were oh my goodness, technology sometimes just doesn't work with you. Man alive. Well, we'll just keep talking and hope nobody notices. The whole point of going through and looking at these is trying to look for patterns and see what we can come up with. Okay, so the first thing that you might try and do is pull out a periodic table. And I trusted you so little that I had a pause in the video just for you. Okay, so now that you've got that periodic table in front of you, you should be able to match up the patterns that you see on the periodic table to predict something about where we might be asking a question right now. And hopefully, the question that you've come up with is what element is in the gray box. Okay, and that element would be potassium or K. Okay, and now we've got a variety of questions because we could now ask what is a predicted atomic radius, a predicted density, melting point, and atomic mass. Because atomic mass was the last one on this list, let's go ahead and take a look at it and come up with a prediction. What we're noticing as we move down the column, which that's probably what you're seeing on your periodic table, hopefully, is that our atomic mass gets bigger. Okay, so cool. That's neat. How much bigger does it get? Well, if we go, we're talking 7 to 23. Was that 16? For those of you at home who can shout no, that's fine. We're looking at approximate. 85 to 132, what is that, 15 and 30, 45? So if we're looking at these jumps, they aren't the exact same. They're getting progressively larger. So a decent guess here might be to pick something in between there and say it goes up by, 28. Okay, so we could say that mass might be, as a guess, would be 23 plus 28, 3 and 8. Man, this is how good my math is. 51. So we might guess we're getting a 51 mass. That would be a reasonable guess based off of the data that we see within this table. We could factor in other things to improve that, but this is the data we've got. That's what I want you to be thinking about and addressing when we go through and look at these patterns. So we should be able to do the same thing to, say, melting point, or to density, or to atomic radius. Okay? So that's what I want you to do, is look for those trends and kind of come up with a reasonable explanation for the analysis that you're giving. Okay? It does not have to be correct, which is where we're going to get a little bit of a curveball here when we go through and pop up with an exam question that could potentially show up. And for those of you watching, you may have just noticed something bizarre that just happened at the bottom of the screen. Don't worry about it. Given the above information, what would be a reasonable density for potassium? Okay, so again, we have to remember that potassium was our gray box. Our density is here. We have a bunch of excess information. So what we need to do is selectively ignore that excess information because that's not going to be useful to contributing to our answer. And what we'd now go through and do is the same process that we went through and did on the other side and try and come up with a reasonable guess for density. So let's fire away. And now that we're back from that little quiz question, let's go ahead and see what our answer is. And that's where, if people were paying attention really carefully, we might see there's a little weird note at the bottom of that, and let's remove that black box. Cool, potassium is exactly where we said it would be. The density comes out to be 0.086. And I'm going to have a hopefully fairly solid guess that you guessed B, as 1.23 is a reasonable guess for density. Okay. Are you correct? Correct in what sense? Correct in the reality? No. 0.86 is not even close to 1.23. And if we push this even further, let's consider what we went through and did. 0.53 to 0.97, it went up. 0.5153 to 1.87, it went up. What happened when we go from sodium to potassium? It went down. That's going counter to the trend. So that's kind of bizarre. So what do we do with this question on an exam then? Okay, what should the answer be? Well, in the context that we were given, the answer was B. Okay? The information that we had at hand caused us to say that the density increased. You should be able to come up with those predictions. It's not impossible to come up with a guess because we have solid information. Saying it was 1.71 doesn't make any sense with the given information because that's saying the density increased far beyond the increases anywhere else. So saying 1.71 doesn't make sense. Saying 0.72, again, doesn't make sense with the data that we had at hand. We saw that the density increased. So 0.72 doesn't make sense either. The only answer that made sense with the data that we had was 1.23. Just because we are wrong doesn't mean our analysis was incorrect. It meant that our analysis, our hypothesis, was missing some piece of information that caused a mismatch with reality. What I want you to be able to do is to process the information given, not try and find the answer, because that's not the point. Okay? The point is trying to learn from the data at hand. It's a challenging concept to get across, okay? But that's what I want you to kind of push for and aim for when you're going through and dealing with questions, both in the exam and with homework. Okay? So let's take a look at another one for trends, predicting chemical properties. One of the interesting things that we found when we're looking at members of a family was also known as a group, which was found in the vertical column. Okay, so when we're looking at members of a family or the column on a periodic table, members in the family have the same properties. Okay, or very similar properties. Okay, why does this become important for us? Well, let's consider something. The alkali metals, when they react with oxygen, all form the general pattern of two metals to one oxygen atom. So if we go through and look at them, they're all matching that. So we can use some information about where an element is found on the periodic table and say we react it with chlorine. Okay? We don't know how chlorine reacts with all elements, and maybe we don't know how it's supposed to react with chlorine. Okay? But we do know how a member in its family reacts with chlorine. We now have an accurate way to predict what should happen to it. Okay? This can be kind of pictorially shown, okay, with the sequence of GIFs. Lithium, when thrown into water, you get this little kind of spark and bubble. Okay? We scale this up. I believe that one's sodium. Potassium, note the response is getting a little bit stronger each time. Rubidium is darn near explosive, and cesium pretty much just takes out the entire container. So it's not saying the chemistry is identical. It's saying it's similar. Okay, we see those similar patterns behind it. Okay, some of that difference in reactivity has to do with its electronic structure, the electronic structure that we don't know about yet. So I'll try and remember to come back and ask a question about why we would expect cesium to be so much more reactive than we would lithium. Okay, but what I would like you to pause and consider here is a little question. Write a possible exam question about predicting chemical properties. To consider when you go through and do this is it shouldn't be explicit. Okay, we want something to actually make the question tricky. For instance, if I had just provided the list of lithium, sodium, potassium, rubidium, but not cesium, and said what would be the expected bonding with oxygen with cesium. Okay, so CSO2 is very clearly what we're fishing for. What would the other multiple choice answers be? Okay? If you looked at the question, there's nothing to suggest any other formula. You don't have to know chemistry behind this. All you have to know is what is the pattern of the letters and the numbers. Okay? So that's not a particularly good question. Okay? Consider that when you go through and try and come up with an exam question of your own. Thanks for trying that. It is challenging, but I want you to at least consider it. Okay? The next thing we'll go through and do is look at some more periodic trends, which is kind of a cliffhanger one. The periodic table means that properties are similar and they follow regular patterns. Okay? So one of those patterns that can come up is the size of an atom or an atomic radius. Okay? And this is a fun kind of thing to consider here. So before we start thinking about what would be that trend, let's consider what we know about our atom. So first and foremost, what is being measured when we say size? Okay, so let's try it again. Because you're all in your own little bubble of your own world, if I asked you, what is your size? That could be an awkward question. Okay, and I'm probably going to get a variety of different responses. You know, A, 6, 200, okay? Those numbers without their units, intentionally in this case, don't really mean a whole lot, okay? But if you had some context about what would be tied to those, that could change things. So how do we decide what size is? Okay, so size in the atomic world, okay, or in the chemical world is talking about radius. How big is that atom? So if we're looking at that little circle that I'm hiding out in, okay, the size is how big around it is. Okay? It's not talking about how heavy that ball is. Okay? Because right now it didn't have any mass in it. Okay? But it's not talking about the weight. It's just talking about the volume. Okay? Now, why does that become important? Well, which subatomic particle is now going to be responsible for that size? We had 3 of them. What were those 3 particles? Proton, neutron, and electron. Proton and neutron both contribute mass because we said size was about radius, not mass. Those aren't large contributors unless they're contributing to the overall size of the particle. Where do the proton and the neutron exist? In the nucleus, which is a marble in the superdome. AKA, not them. That's not the middle one, by the way, just in case you were wondering. The electron is the only thing that's left. Electrons contribute to size. Okay? Where did we say electrons exist? Outside the nucleus. Okay? Because we haven't defined where outside the nucleus, we now in kind of an issue. We're just saying they're out there, which means more electrons, presumably the bigger it gets. Less electrons, the smaller it gets. Okay, that seems reasonable. So let's go ahead and take a look at some trends. Atomic radius increases as we go down a group. So down a periodic table, we get a larger radius. Well, did that jive with our initial assessment? As we go down the column, we get more electrons. Hey, that makes sense. It gets bigger. But now the fun one. Atomic radius decreases as we go, presumably you're seeing this the same way I am, so it's left to right, okay? And as we go left to right, we increase the number of electrons. So it should get bigger, not smaller. So there's something not working here. Okay, and for those of you saying, but the nucleus gets bigger, okay, and that's why it gets smaller. What about down the column, dude? When you go down a column, what happens to the nucleus too? It also gets bigger. So there's something about our atomic theory that doesn't actually explain what's happening with our atomic radius. Okay, and to do that, we really have to dig into electronic structure, which means jumping back to chapter 4. But before we do that, let's just take a look pictorially at what we're talking about here. If we go through it and again kind of look at this, what are we seeing? Maybe. Just have to look down when I go through and do it. When we go down the column, what happens to the radius? Look, it's progressively getting a little bit bigger and bigger. We're trying to show that pictorially here. Okay. If you don't like pictures and you like numbers, 0.152, 0.86, notice it's getting bigger. Okay, so down the column, but that trend kind of made sense already. When we go left to right, you can also see that our size is getting significantly smaller as well. And so there we encounter our big question. Why would it get smaller? Well, if it's due to the electrons, we are getting more electrons that direction. Why would it get smaller before it gets larger? And so there's something not connecting correctly there. And I'm 90% certain that is the last slide I wanted to talk about, but just in case, another picture. Okay, atomic radius and officially metallic character. These are two trends that I would recommend that you start to do. Get your periodic table out, okay? Get a printout of it and start drawing these trends on it so that you know them. Okay, don't just draw arrows, because I've seen people do things like that. They just go, oh, atomic radius, and then show arrows. Well, what the hell does that mean? Does that mean the atomic radius got bigger or smaller? Okay, what are you referencing? Okay, so make sure that you've got it solidly labeled out. Okay, and then with that, I'm like now 99%. Yeah, we're into the next lecture. So again, here's our periodic table showing you those trends. Recommend that you memorize it. We will be adding some more trends across the periodic table. And with that, a little over 30 minutes. I tried to go fast. I apologize. We'll go ahead and stop.